Section: Introduction. In this section, we highlight the significant progress made in multimodal intelligence, particularly in understanding and generation. We note that multimodal large language models, such as LLAVA, excel in tasks that combine vision and language, like visual question answering. On the generation side, denoising diffusion probabilistic models have transformed how we create images and videos from text. Given these advancements, we see a natural opportunity to connect these two areas. Recent efforts have attempted to merge expert models from both domains into a single system capable of both understanding and generating multimodal content. However, many of these approaches treat understanding and generation separately, often relying on distinct models for each task. For example, NextGPT uses a language model for understanding but requires a separate model for image generation. This raises an important question: can we create a single model that effectively handles both tasks? Recently, Chameleon has shown that this is indeed possible by integrating different modalities early on to generate text and image tokens using a unified autoregressive approach. While autoregressive modeling works well for text, it is less clear if it is the best method for images, especially given the high number of sampling steps needed for image generation. We propose a new paradigm where text is treated as discrete tokens modeled auto-regressively, similar to large language models, while image pixels are handled using denoising diffusion. However, merging these two techniques into one model is challenging due to the differences between text and image representations. Our model, ShowO, builds on a pre-trained language model and incorporates autoregressive capabilities for text reasoning. We utilize discrete denoising diffusion to model image tokens, eliminating the need for separate text encoders. To manage various input types, we employ both text and image tokenizers, along with a unified prompting strategy to process these tokens. ShowO can answer questions based on images auto-regressively and generate images from text using discrete denoising diffusion. It shows comparable or even superior performance to individual models with similar or larger parameter counts across benchmarks. Notably, ShowO requires about 20 times fewer sampling steps for image generation, indicating its efficiency. Additionally, ShowO supports various applications, such as text-based inpainting and extrapolation, without needing fine-tuning. We also explore its potential for mixed modality generation, like creating video keyframes from text descriptions, showcasing its capability for long-form video generation. We investigate how different image representations affect multimodal understanding, providing insights for future unified model designs. Our comparison of ShowO with existing methods reveals its flexibility in addressing multimodal tasks effectively. In summary, our main contributions include the introduction of ShowO as a unified model for multimodal understanding and generation, the innovative integration of autoregressive and discrete diffusion modeling, and the demonstration of its performance across various benchmarks and applications. We also provide insights into the impact of representation types on multimodal understanding, paving the way for future improvements. Section Summary. In this section, we introduce ShowO, a unified model that integrates multimodal understanding and generation by combining autoregressive and discrete diffusion modeling, allowing it to handle both text and images effectively. ShowO demonstrates superior performance compared to individual models, supports various applications without fine-tuning, and provides insights into the impact of different image representations on multimodal understanding. Section: Related Work. In this section, we discuss related work in multimodal understanding and generation. We have seen significant progress in large language models, LLMs, which has led to the creation of multimodal large language models, MLLMs. Early examples like LLAVA, MiniGPT-4, and InstructBlip show impressive capabilities in understanding multiple modalities. These studies have integrated LLMs into multimodal contexts by projecting features from specialized encoders, such as CLIP, into the LLM input space, allowing for better understanding and reasoning. However, while these models excel in visual perception, they mainly generate text and do not produce multimodal outputs. In terms of visual generation, autoregressive models, particularly transformer models, have been successful in natural language processing. Some studies have applied autoregressive techniques to learn the relationships between image pixels for generating images and videos. For example, VideoPoet uses a decoder-only structure to create high-quality videos from various inputs. More recently, Llama Gen has shown that large language models can also model image tokens effectively for generating images based on specific conditions. Diffusion models have gained attention for their strong performance in generating images and videos from text. These models typically operate in a continuous latent space, predicting noise added to these representations. Some methods, like D3PM and MaskGIT, use a discrete corruption process instead. In this context, images are represented as sequences of discrete tokens, each linked to a category. During training, some tokens are masked, and the model learns to predict their original values. Our work, Show-O, adopts this discrete diffusion approach for visual generation. We also note the rise of unified multimodal language models that can both understand and generate content. Some models combine continuous representations with text tokens for image generation. SeedX, for instance, proposes a versatile system that integrates multimodal understanding and generation by combining image representations with text tokens for predictions. Chameleon introduces models that treat all modalities as discrete tokens and trains them in an end-to-end manner. In our approach, we also use discrete tokens but focus on a discrete diffusion process for visual generation instead of autoregressive modeling. Our goal is to create a unified model that incorporates both autoregressive and diffusion modeling for multimodal understanding and generation. This task presents several challenges, including defining the input-output space, unifying different input data types, integrating both modeling approaches, and effectively training the model. We present our solutions through Show-O, addressing these challenges step by step. First, we define the input-output space by tokenizing text and image data into discrete tokens. Next, we introduce the Show-O architecture and a unified prompting strategy for structuring input data. We also explain how to combine autoregressive and diffusion modeling within a single framework. Finally, we outline a three-stage training pipeline to train the unified model effectively. For tokenization, since Show-O is based on pre-trained LLMs, we perform unified learning in a discrete space, maintaining a vocabulary of discrete text and image tokens. For text, we use the same tokenizer as the pre-trained LLM without changes. For images, we train a quantizer using around 35 million images, creating a codebook that encodes images into discrete tokens. This approach is inspired by MAGVITV2, which we plan to explore further for video tokenization. We also consider using different tokenizers for understanding and generation. Our default Show-O uses discrete image tokens for both tasks, and we will provide more details in the following sections. Section Summary. In this section, we review advancements in multimodal large language models, MLLMs, that integrate visual and textual understanding, highlighting their reliance on autoregressive modeling and the limitations in generating multimodal outputs. We also discuss the development of unified models like Show-O, which combines autoregressive and diffusion modeling for enhanced multimodal understanding and generation, addressing challenges in input-output space definition and training methodologies. Section: Architecture. In this section, we describe our architecture. Show-O adopts the structure of existing large language models, making no changes except for adding a QK norm operation to each layer. We initialize Show-O using the weights from a pre-trained model and increase the embedding layer size by adding 8,192 new learnable embeddings for discrete image tokens. Unlike advanced diffusion models that need a separate text encoder, Show-O can encode text information on its own for text-to-image generation. To facilitate unified learning across different types of data, we create a unified prompting strategy. For an image-text pair, we first break it down into image tokens and text tokens. We then organize these tokens into an input sequence based on the task type. We use specific task tokens to indicate the learning task, along with special tokens to mark the start and end of text and image tokens. This design allows us to effectively process various input data for multimodal understanding and generation, enabling seamless learning across different tasks. Once trained, we can prompt Show-O to perform various vision language tasks, such as visual question answering and text-to-image generation. We introduce an omni-attention mechanism that differs from existing models that only process sequences in a linear manner. This mechanism allows Show-O to handle different types of signals flexibly. It combines causal and full attention based on the input format. For text tokens, we use causal attention, while for image tokens, we apply full attention, allowing all tokens to interact with each other. This setup enhances multimodal understanding and improves image generation efficiency by reducing the number of sampling steps. It also supports various applications like inpainting and extrapolation without needing fine-tuning. When only text tokens are present, the mechanism simplifies to causal attention. For training, we use two objectives: Next Token Prediction, NTP, and Mask Token Prediction, MTP. We aim to maximize the likelihood of text tokens using standard language modeling techniques. If the input consists solely of text tokens, we do not include any conditional terms for image tokens. Our approach integrates the generative paradigm of mask-GIT for seamless diffusion modeling. We create a mask sequence by randomly replacing some image tokens with a mask token and then aim to reconstruct the original image tokens based on the unmasked tokens and preceding text tokens. We also incorporate a strategy to randomly replace some text tokens with a null text to enhance training. The overall training loss combines the losses from MTP and NTP, weighted by a hyperparameter. Section Summary. In this section, we describe the architecture of Show-O, which builds on existing LLMs by adding a QK norm operation and expanding the embedding layer for image tokens, allowing it to inherently encode text for text-to-image generation without needing an additional text encoder. We also introduce a unified prompting strategy for multimodal input, an omni-attention mechanism for flexible signal processing, and dual training objectives to enhance performance across various vision language tasks. Section: Training Pipeline. In this section, we outline our training pipeline for Show-O. Since the image token embeddings are newly initialized, we require extensive pre-training to ensure effective multimodal understanding and generation. We also remove the text encoder for extracting text embeddings in text-to-image generation, which complicates the alignment between text and image content. To address this, we adopt a three-stage training approach. 1. Image token embedding and pixel dependency learning. We utilize the refined web dataset to train Show-O while preserving its language modeling capabilities. Additionally, we use the ImageNet-1K dataset and 35 million image text pairs for class conditional image generation and image captioning. In this stage, we focus on learning new embeddings for image tokens, understanding pixel dependencies for image generation, and aligning images with text for captioning. 2. Image-text alignment for multimodal understanding and generation. Building on the pre-trained weights, we shift our focus to training text-to-image generation using the 35 million image text pairs. This stage emphasizes aligning images and text for both captioning and generation tasks. 3. High-quality data fine-tuning. Finally, we refine the pre-trained Show-O model by incorporating filtered high-quality image text pairs for text-to-image generation and instructional data for enhanced multimodal understanding and mixed modality generation. For our experimental setup, we use three types of datasets. Text-only data. We leverage the refined web dataset, which contains about 1 billion instances and 2.8 terabytes of curated text data, to maintain the text reasoning abilities of the pre-trained model. Image data with class names. We train Show-O on 1.28 million images from the ImageNet-1K dataset to learn pixel dependencies. Image text data. We compile around 35 million image text pairs from publicly available datasets like CC12M, SA1B, and LAION Aesthetics 12M for multimodal tasks. We also use shared GPT-4 volts for recaptioning these datasets and include high-quality datasets for final fine-tuning. For evaluation, we assess Show-O's multimodal understanding on various benchmarks and use Frechet inception distance on the MSCOCO dataset to measure generation fidelity. We compare our results with models focused on understanding, generation, and unified models. In terms of implementation, we first conduct joint training using the refined web dataset, the 35 million image text pairs, and the ImageNet-1K dataset over 500,000 steps. We then switch to training for text-to-image generation for an additional 1 million steps. Our base model is trained on 48 A100 GPS with a total batch size of 1,152, using the ADAM-W optimizer with specific parameters. Finally, we fine-tune Show-O with high-quality image text pairs and follow the configuration of LLAVA v1.5 for instruction tuning. During inference, we compute logits for masked tokens, and the current version of Show-O is based on PHI 1.5. We also explore using continuous image representations from pre-trained models for multimodal understanding. Section Summary. In this section, we outline our training pipeline for Show-O, which involves a three-stage approach to achieve effective multimodal understanding and generation, starting with image token embedding and pixel dependency learning, followed by image-text alignment, and concluding with high-quality data fine-tuning. We utilize diverse datasets, including refined web, ImageNet-1K, and 35M image text pairs, and implement a comprehensive evaluation strategy to assess Show-O's performance against various benchmarks and models. Section: Quantitative Evaluation. In this section, we evaluate the quantitative performance of Show-O on various public benchmarks, focusing on tasks like image captioning and visual question answering. First, we note that Show-O is based on PHI 1.5, and we use LLAVA v1.5 Phi 1.5 as our direct baseline for understanding. Our results show that Show-O performs similarly to this baseline, which is specifically designed for multimodal understanding. This suggests that our framework has strong potential to combine understanding and generation in one model. Next, when we compare Show-O to other understanding-only models like InstructBlip, QuenVLChat, and MPLU-GAL2, we find that our model, which is smaller in size, still achieves competitive results on benchmarks such as Pope, Me, Flickr 30K, and performs even better on GQA. Additionally, when we look at larger unified models like NextGPT-13b and Chameleon-34b, Show-O still shows decent performance on Flickr 30K and significantly outperforms on VQA-v2. These encouraging results lead us to see Show-O as a promising next-generation model for integrating understanding and generation, with the potential for state-of-the-art performance. For qualitative results, we demonstrate Show-O's ability in visual question answering and compare it with Chameleon and SeedX. We observe that Show-O can accurately describe images and answer questions, even about unusual features. For instance, while all models provide good descriptions, Show-O gives a more precise answer regarding the unusual aspects of an image compared to the others. In terms of visual generation, we present the zero-shot FID results for Show-O on the MS-COCO 30K dataset. We find that Show-O, with only 1.3 billion parameters and 35 million training images, achieves a better FID score than larger models like Glide and DAL-E2. Although GigaGAN, Imagine, and Raphael perform slightly better, they are much larger and trained on more data. This indicates that Show-O can compete with or even outperform individual generation models of similar or larger sizes. However, we acknowledge that the FID score on MS-COCO 30K may not fully reflect generation quality, as existing models are often fine-tuned on high-quality images that differ from the MSCOCO dataset. Finally, we assess Show-O's text-to-image generation capabilities on the Gen Eval benchmark across 6 dimensions. We find that Show-O outperforms similarly sized models like LDM and even does better than DAL-E2, which is significantly larger. This suggests that our unified model's generative abilities are on par with or exceed those of specialized models. Overall, Show-O shows significant improvements compared to other unified models as well. Section Summary. In this section, we evaluate the multimodal understanding and generation capabilities of Show-O, demonstrating that it performs comparably to specialized models like LLAVA v1.5 Phi 1.5 while being smaller in size, and achieves competitive results on various benchmarks. Additionally, our model shows strong performance in text-to-image generation, surpassing larger models like DAL-E2 and indicating its potential as a next-generation unified framework for multimodal tasks. Section: Qualitative Results. In this section, we present qualitative comparisons of our model, Show-O, with various diffusion-based models like SDV 1.5 and SDXL, as well as autoregressive models such as LGen, and unified models including LWM and SeedX. We observe that Show-O can generate realistic images that align well with both short and long text prompts. Compared to SDV 1.5 and LlamaGen, Show-O offers superior visual quality and better alignment with the text. For example, while SDV 1.5 and LlamaGen fail to capture elements like sunsets and blue domes, Show-O successfully includes these details. When compared to SDXL, Show-O maintains similar visual quality and alignment, as seen in prompts like a rally car race against a vibrant sunset. Additional samples generated by Show-O are available for review. We also highlight Show-O's capabilities in text-guided inpainting and extrapolation without needing fine-tuning. For instance, we demonstrate how Show-O can transform a red trolley car into a blue sports car based on a user's text prompt. Furthermore, it can extend images both horizontally and vertically, adding new elements like red wildflowers. The pixels in both inpainted and extrapolated areas remain consistent with the original image, showcasing Show-O's advantages over auto-regressive models. Next, we explore Show-O's ability to generate mixed modality outputs, combining text descriptions and video keyframes from the Gen How-To dataset. By processing a sequence of text and video keyframes, Show-O predicts the next tokens based on prior information, allowing for the generation of coherent video keyframes. We find that when given prompts, Show-O produces consistent keyframes, and when trained with instructional examples, it can generate relevant keyframes for tasks like making avocado and apple juice. This suggests potential for extending our model to long video generation, where it can iteratively create sequences of videos. In our ablation studies, we analyze different design choices for input to enhance multimodal understanding. We find that using continuous image representations from pre-trained models like MAGVI-TV2 and ClipVid improves performance. Our experiments reveal that the ClipVid encoder, trained on a larger dataset, significantly outperforms MAGVI-TV2 in multimodal understanding. This is largely due to the discriminative loss used in ClipVid, which facilitates better adaptation for our tasks. Section Summary. In this section, we present qualitative comparisons of our model, Show-O, with various diffusion and autoregressive models, demonstrating its superior visual quality and image-text alignment in generating realistic images from text prompts. Additionally, we highlight Show-O's capabilities in text-guided inpainting, extrapolation, and mixed modality generation of video keyframes and captions, showcasing its potential for consistent and diverse visual content creation without the need for fine-tuning. Section: Impact of various representations for multimodal understanding. In this section, we examine the impact of different representations on multimodal understanding. Typically, models like LLAVA extract image representations and align them in a continuous space. However, image tokenizers like MAGVI-TV2 produce discrete image tokens. We compare these two types of inputs, continuous representations and discrete tokens, in our multimodal understanding experiments. In experiments 6 and 7, we use the pre-trained MAGVI-TV2 to extract discrete tokens and train an embedding layer to convert these tokens into the continuous space of the language model. In experiments 4 and 5, we adjust MAGVI-TV2 to provide continuous representations without quantization, following Java's cross-modal projection layer setup. Our findings show that discrete tokens perform significantly worse on most benchmarks compared to continuous representations. We believe this performance gap arises because popular multimodal datasets, like LLAVA pretrain -558K, do not effectively align discrete tokens with the language space, resulting in poor cross-modal understanding. Continuous representations, on the other hand, are easier to align since they already exist in a well-structured embedding space. Next, we discuss the impact of unified pre-training for multimodal understanding. Our training process involves a two-stage unified pre-training to learn image token embedding and image text alignment. We analyze how this unified pre-training affects different vision encoders and representation types. For clip-vit with continuous representations, our comparison between experiments 2 and 3 indicates that unified pre-training has a slight negative effect, as we observe minor performance drops on most benchmarks. We hypothesize that the pre-training with MAGVI-TV2 tokens and the tuning with clip-vit occur in nearly independent dimensions, allowing the backbone to maintain compatibility between the two tasks. For MAGVI-TV2 with continuous representations, our comparison of experiments 4 and 5 shows a performance improvement due to unified pre-training, even though the pre-training used discrete tokens. This supports our hypothesis that unified pre-training enhances multimodal understanding through diverse interactions. When we look at MAGVI-TV2 with discrete tokens, the comparison between experiments 6 and 7 reveals a significant boost in performance, which we attribute to the unified pre-training's ability to learn better cross-modal alignment with large-scale data. We also present qualitative examples to illustrate the effects of sampling steps and classifier-free guidance in text-to-image generation. We generate images at a resolution of 256 by 256 pixels with varying sampling steps. With just 2 steps, we can create an image loosely related to the prompt. Increasing the steps to 8 results in an image that closely matches the prompt, while 16 steps yield a more detailed and realistic image. In contrast, auto-regressive models require 256 steps to achieve similar results, which is 16 times more than our method. Regarding classifier-free guidance, we show how different guidance scales affect the generated images. Without classifier-free guidance, the images lack detail and objects. As we increase the guidance scale, the images become more diverse and aligned with the text prompt. Lastly, we address some failure cases of our model, SHOW-O, in multimodal understanding and generation. We highlight challenges in text recognition and object counting, such as difficulties in identifying the phrase, closing down, and generating the term, mardfly. These issues stem from a lack of specific data for these scenarios, as our model relies on a limited set of image-text pairs from publicly available datasets. We believe that enhancing this data will help address these failure modes in SHOW-O, which we plan to explore in the future.